All right. So we kind of connected our problem that we want to solve, the security problem with the RSA, and we already know the connection from RSA to factorization or computing the phi n, those things you already know. This is how, the overall proof would look like. So let me say it briefly one more time, very quickly. So we are going to reduce or computing the ETH root to breaking the RSA signature, saying that if somebody can break the RSA signature, by breaking we mean that this attacker can provide us a forged signature for any message, then we can use that forged message to compute the ETH root that we know that is hard. So this is the entire thing that we are going to do today. All right, this slide looks like a bit texy, but don't worry, it's a bit messy, but we need all this thing together to really understand what is going on here. Um, so we start with the theorem that, if you look into any paper, you will start to see this sort of text, in the theorem. So it is good for you to also get familiar with how to understand this. So it starts by saying that under the RSA assumption, under that the RSA problem is a hard assumption. The full domain hash RSA. Now we understand what does that full domain hash function means. Signature scheme is existential unforgeable. So existential unforgeable means that it is not even possible for somebody to, forge any message. It is not possible at all. Sometimes you see some other words such as selectively forgeable, which means that somebody can, on other those kind of signature schemes that we won't use them in practice. It means that they can forge some random messages, but they cannot forge a given message, right? So those are weaker security proof, weaker schemes. The one that are very strong cryptographic scheme are for signature scheme, are the one that are existential unforgeable. That it means that it is not even possible to forge any random message. Not, so this is better than relying on something that says that you cannot forge any meaningful message. So that is a very weak assumption. Anyways, we continue with this against the adaptive chosen message attack. So adaptive chosen message attack. Remember that we talk about chosen message attack. So that attacker choose a message and then have or signature scheme to sign that message for this attacker, and then see the result, and then the attacker can basically choose another message and have the scheme to sign that one, and so on and so forth. So we let this to appear for some number of queries, and then after that the attacker should provide us a forgery, right? If the forgery is correct, then he would win, and if it is incorrect, then he will lose, right? So we would allow this attacker to even interact with our signature scheme and provide him some signature of the messages of his choice. And this also shows that our scheme is quite strong. And then in the random oracle mode. So these red ones are very important. In the random oracle mode means that now you get the understanding that so there are some objects that we are using in this crypto system that they might not exist in the real world. So the moment that you see the random oracle model in some crypto system proof, what does that mean? The very first thing that you want to assumption that you want to have is that this is basically a theoretical work. You should not use this work in practice, and especially we are talking about we are in the applied cryptographic course. So I brought this example to show you that after we go through the proof, you will get convinced and everything is nice and neat, but underneath the system, we are using some oracles that unfortunately we don't have access to them in practice. So in practice, we cannot disprove it, and also we at the same time we cannot prove that they still stay secure. So we are in like a world of unknown, and that is why for most of the crypto systems that you see this random oracle model, they proven under that, so we will not use them in practice. We don't recommend them. So the proof start with some clearing out some assumptions that we have. So we assume that we have a forger. So the forger, we start to show him with the capital F. And then on the top, you see that this forger, we give him access to two oracles. Oracle of the hash function and oracle of the signature, right? So we are going to expand on them very soon. So the forger would take input the public key, just like everybody else, that the signature scheme is going to sign some messages. So we need the public key to be able to verify the messages, the signatures. So then we would allow the F to query or hash function, the hash oracle. Now, we know how to instantiate this hash oracle. We need to create that table, all those stuff that we discussed about. So every time that you query the hash oracle, we would generate a random value for it. And then, so it would generate a random hash over the ZN. So we would choose one of these elements, and then we would store it in the database. And given that if this attacker query the same message again, so we can check or look up table and then return the value that we've returned for it before. So this one is we are quite familiar with so far. And then now we are talking about the signing oracle. So after we query the message for its signature for its hash function first, and then we can go back and ask the signing oracle that, hey, what is the signature for this message MJ? We pass this one to the signature oracle, and then the signature oracle is supposed to do this sort of computation, right? So he would use his private key to sign the message and then return N for us. And after we have played this game, we allow our attacker, we give him the input, we let him to play with the hash function, we let him play with the signature hash function, with the signing oracle. And after some time that this attacker has played with the system, then it is the time for him to find a weakness and say that, what, based on this correlation that I found over here, or sometimes he craft messages in a special way that he can use it to generate sign other messages. And if the crypto system is weak enough, he would be able to do that. Then at the end, no matter what technique the forger uses, he is supposed to give a valid signature on some message. We call it valid. Let me make it clear. Valid M and S, because M should not equal to any of those messages, M1, M2, all the way to ML, that was queried to the signing oracle. Okay, so it means that this guy, the attacker, after he is claiming that he forged the signature, it is okay for him to get the hash of the message from the hashing oracle, but of course it shouldn't be the case that he got he asked for the signature of this message from the signing oracle. Then of course we provide him the signature, and he provide this as a forgery. It is not acceptable because we were the one who compute this signature for him. So we expect him to provide the signature of some message other than those that we already provide him the signature, a sample signature, right? So this is the condition that we call it a valid signature. So we need to be careful about this one. All right. So let's discuss now in very high level how this forgery would look like, and what we are going to spend our time today. So the best way that we can discuss that is to talk about the reduction diagram. So the diagram is we have some attacker over here that this attacker is saying that we have a RSA hard problem. So given n, e, and y, we want to do something and compute the eth root of y, right? Mod n. But well, we don't know how to do this one, right? So the idea is that we are reducing this to this RSA signature problem. So we are passing our N and E, the public key, to this forger, right? So the forger would receive this N and E, and then we allow the forger to play with our hash oracle, so some MI to our hash oracle, and then this guy would return the hash of MI. And also we show that he would be able to play with the signature oracle, and then with that we are providing him some signature of J, right? So that after that he did his computation, then this guy would output a forged signature. So he would output some M and S, some valid signature, that we call this one a forged signature, right? So we are going to use this forged signature to compute this eth root that we didn't know how to compute in the first place. So this is going to be our reduction diagram. So the whole idea now here is that so we are trying to make this algorithm A. The entire goal is that, well, we know that this is a hard assumption, but it looked like that if we can have this entire thing to work out, and we design this digital signature, and then if we can create this algorithm A in practice, that he go and interact with this forger, and the forger output a forged signature, then we can use this A algorithm to solve RSA problem, to compute the eth root for any input, right? So given this interaction, it looked like that we can design an A algorithm that, given or forger with the access with the hash function and the oracle of the signature, and also N and E and Y, right? So the input to the hard problem, then this guy can go ahead and make this interaction happen. This algorithm A calls the forger, and the forger does his job, and then you provide the valid signature, and then at the end we turn that one into computing the eth root of Y, right? So I can compute the eth root of Y mod N. So this is our goal. So the question is that, can we create this A? So it looked like that this reduction diagram works. So can we turn A to an algorithm that can every time that we call it, he just does the entire thing by itself? So we want to design that algorithm, we are given to this algorithm, this forger with this access to these oracles, and then this input, and then the algorithm would go and interact with this forger. The A would have to provide the oracle of signature and oracle of the hash function to the forger and all those stuff, and then the forger would provide us the signature. So what we want to do is to just create this A function that, given this input, the A would take care of the rest, right? And it would just compute the eth root for us. So we are trying to convert A into a real algorithm without oracle. right? So we somehow, when we want to turn it into the real algorithm, we also need to get rid of the oracles, right? We cannot assume that somebody would give us that oracle. So who's that somebody? When we are writing A as an algorithm that we suppose that we can run it on our computer, then we have to find a way to, provide him to instantiate that hash oracle and the signature oracle. So for a hash oracle, right now we have an idea. If we have that table, we have a rough idea with the previous slides. How do we do that? So it looked like that is feasible. We just need to make a lookup table and generate random numbers. So we can create that hash function now. But the biggest question is that the signature oracle, right? That is something we don't know. So then the challenges that we have is that we have to answer the hash function oracle queries and then the signature queries without knowing the D. This D is our private key, right? So, well, it is becoming a bit challenging now, right? We know that we want to instantiate this A in practice, but going back to the previous slide, in order to provide, this one we know, like the hash function we know how to do, but the signature one, when somebody passes you a message to sign, well, we need to know the secret key D so that we compute the hash of M to the D mod N, right? But now, unfortunately, our scenario here is that we do not have access to that private key because all we have A as the input is this information, right? If we knew the D, then why would we have to deal with this, right? We would just compute Y to the D, and then we would be able to compute X directly. So that's the point, that we need to find a trick so that we can also instantiate this signing oracle, and that is what we are going to spend some of our time today. So let me put that in more clear text. So our goal now is to construct a polynomial time algorithm, of course, A, that solves the RSA problem. A takes as input this N, E, and Y, the challenge that we need to solve. And then we know that A would use some forger F, but F needs hash oracle and signature oracle, but right now, well, the point is we don't have those oracles. We have to create them. So that's the challenge. So in this case, A would call this forger with this input N and E to get the forged message. Let's call it M prime and sigma prime. And then in order for F to work, the forger to work, we need to provide him, answer his hash queries. We also need to answer his signature queries of this format. But the problem is that this one is okay to do, this one is okay to do, but this one is something that we do not know how to do it because we don't know how to compute the signature without the private key. And once everything is done, then we can return the ETH root. Once we get the forged signature, we are able to compute that. And I will show you how we would be able to do that computation. There are some rules in the game. We always, have to have some small assumptions, which is fine. So without lose of generality, we assume that our forger F would, he would never query some messages twice to the oracle of hash function. even though he does, I think it's fine for this construction because we have a lookup table and then we are able to just return what he has queried before. But we are just saying without lose of generality, so it doesn't. Some of them doesn't really matter, but this one matter that when somebody when the forger try to ask or signature oracle to sign a message for him, then this message should have been queried to the hash oracle before, right? Because or hash oracle is now returning random values for every time you ask for a hash of some message. So before you go ahead to compute the signature, you have to compute the hash of this message first, and then you can compute the signature for it, right? So we assume that the attacker, the forger, would do this, follow the order. And if it doesn't follow the order, we can just abort in algorithm A somewhere. We can just return null, right? So we say that the forger is not did something illegal, right? So we abort at that point. And then and also the forged message that the attacker is providing, the forger is providing, M should be queried to the hash oracle in the beginning, right? So he cannot come back and return some forged messages that he didn't even query that message to the hash function in the first place. Imagine that you want the forger would say that, oh, this is the message and the signature, and then well, the point is we are generating the hash of the messages in a random fashion, right? So if he didn't query the hash function for that message, then there is a very small probability that he guessed the hash function correctly, right? So that's why we say that it has to be the case that he queried the hash function for that message M before, but probably he didn't query the signing oracle for that message, and that would be the case that we are fine with that. All right, so we are now getting to discuss the details for this algorithm A. So I think we can go two ways. Let me start with the text, and also I will start to draw out things that we want to do very soon. Okay. So for algorithm A, we say that it takes input N, E, and Y. So the very first thing that this a guy would do is that his goal is to return or to compute the eth root of y on n, so that would be the output. This is how he would start to do the things. So the first thing is that he would choose a number t randomly from 1 to r. So the truth is, the first thing that A would do is that he will set up a table. This is our algorithm A. And then, so the first thing that he does is that he chooses the index T from 1 to R. So we suppose that we would have R interactions. We allow R interactions for this forger with our hash function and a signature scheme. So he can make at most R queries. You cannot let, since A has to be polynomial, you can imagine that the number of the queries that we allow our forger to make to the signing or hash oracle cannot be exponential, right? If that is exponential, then our A would become exponential. So our algorithm is polynomial, meaning that we allow at most polynomial number of time of querying. Let's just say R times. So you choose he chooses an index T from 1 to R, and then and then after he chose this one, then he called the forger with input N and E, and then watches what actions F takes or what F asks for it. So the first thing first that he does is that every time that the forger would make a query to the hash function, he take these two steps. So if the forger asks for, this is M, let me make it clear. This is hash of M. So the first thing that he does is that he creates this table. So that he store the computations over. So the first time the attacker, whenever he asks for a hash of some message, we check this one. We try to not answer anything on location T, but for rest of them, we would do this computation. So every time that, let's say this is the M1 and we are not in MT, so let's just go for an easy case. And then every time that the attacker would choose, and let me make clear the T here. This is the index T. Okay. So if we are not on message MT, the way that we are going to answer these queries is as following. Every time that the forger asks for a hash of message or a signature of a message, this is how we would proceed. So he would select an SI from 0 all the way to n-1, a random message, and then computes hash of mi to be hi. We are going to say this is equals to si to the power e mod n. Okay. So now that we are providing this, we are instantiating these forgers. We know that we don't know the secret key D. So we are crafting these things so that we are able to also sign it as well. And then I'm going to say that this M1 and MI and SI is going to be is valid. So I is valid, right? Because remember, how do we sign a message and how do we verify? So let me write it in a different color up here so that in order to sign a message, what you would do is that we compute the hash of M, we raise it to the power D, compute mod N, right? In order to verify message and signature, what we do is that, or let me just use S because we're using S from here on. What we do, we check if hash of M, we compute the hash of M using this one, is equal to S to the power E. Okay. We said that we get the signature, we raise it to the public key mod N, and these two entities should be equal. So, and this is exactly the trick that we use over here. We know that, somebody would take this signature, right? And then whatever signature it is, we raise it to the power E at the end, and that should become equal to the hash of M. So over here, we don't know the D, but we can somehow make this equality to rematch. And then to the I of the forger, this is a valid signature. How do we do so? So we select our signature to be some random value from 0 to n-1, any of those values. And then since we are also creating the value output of the hash function for this message, then we have this power that we can define the output of this hash function to be S to the power E mod N. Okay. So HI over here is going to be, we're gonna fill this out. We are saying that it is going to be S1 to the power E, which is going to be H1, right? And then the signature is just S1, right? So what happens if we provide this information to the forger. The forger would go ahead and ask for signature for this message and hash of this message. So what we do is like we do a trick. We know that in order for the forger to verify, so the forger would look at this one to verify. He takes this message M and S1, and what it does is that he computes this one. He computes H of M, M1, and then this is going to be what? He's going to query this, table, this oracle, and say that what is the hash of M1? We would return, we say that this is S1 to the E, right? And what is the signature? S1. So he's going to do this one. He's going to also compute S1 to the E mod N, right? And guess what? These two things are equal, right? So then the whole thing is correct to the eye of the verifier that, okay, you provide the signature for this message and that is correct. But the truth is the way that we computed over here, we cheated, right? We didn't have the exponent D, we didn't have the secret key, but because we are using random oracle, we are the one who can define what should be the output of the hash function, and we are the one who can decide what should be the output of the signature, right? What should be the signature. And because of that, we just make these two relationship to look the same, so that signature to the power E should equal to the hash to the power to the hash function of M. And because we make that equality in the first place, we know that how to cheat for those stuff. So to the eye of the forger, everything looks okay because we provide a hash function. The output of the hash function has enough length, so to his eyes is fine. And then he asks for the signature of that, and then we see that we also know how to sign it. But the only difference is that every time that he asks for a hash of some message, we also pre-compute the signature at the same time. So we know that later he will come back and ask for the signature of this message. By our construction, we have to do it because we have to select the signature, and then based upon that we set what should be the output of our hash function. So to the eye of the forger, everything is okay, and this we are kind of simulating what an actual signer with access to this private exponent D would do, because everything again look random. We choose a random SI, so this would be some random value, and then when you raise some random value to the power E mod N, so this hash function would also look random, right? So you're raising randomness to some constant exponent, but that doesn't matter because your input is already random. So we are simulating this for the attacker, but the simulation is almost very close to the real world scenario. So forger cannot tell if he's playing with somebody that has access to the secret key, or he's playing with somebody like this simulation with algorithm A. That is the outcome of what we are doing. So the truth is, the forger would ask for more queries, so he would probably, let me use the same color. He would do M2, and then we return him, H2, and then we return him S2, and so on and so forth. So he would do all this computation, and then we would allow and basically return all the queries that he asked for. So MR minus 1, and then we have HR minus 1, and then we have SR minus 1, and finally we have MR, HR, and then SR, right? So everything is the same, but we had this condition that when he asks to answer, the query for the location T that we chose, so that is something that we should go back to. So for every other location that he asked for a query, we won't say anything. For one of those locations that he asked for a message, so empty, we call it empty, the query, the teeth queries, when he asked for that message, this is where, so-called in cryptography, we say we embed the hard assumption. So we embed our hard assumption over here. We set this one to be y, and this one is a question mark. We don't know. So we are hoping that this one is going to forge this, the forger is going to forge or M and then return us some S, right? So that is the trick. It's the second trick that we are going to use over here. So everything is the same. You see that for every other queries that he asks, we genuinely providing him some answers, and then he thinks that he's really playing with somebody that has access to that private key. The only query that we would not answer his signature query if he asks ever is this T location. So we choose a T in the very beginning, and then when he asks for the hash of this message, we just return him Y. What is Y? Y, remember, was the input for our hard problem that we want to solve. A wants to find the eth root of E, right? Y. So for that, we let Y to be the output of our hash function. So guess what happens when we hope that basically forger would provide the forgery for here, and he would be able to sign this message for us, right? The MT. And if he ever be able to sign this message, then we can solve our RSA problem. So let me put it this way, that here there is some non-negligible probability that the forgery that he provide, M is actually equals to MT, right? The message that the forger would at the end provide us for as a forgery is this MT that he queried the hash function before, and then the S that he provides over here, the signature, is actually exactly the eth root of the hash function, right? So this is exactly the eth root of that, which is the our hash function. We let it to be Y, which is the eth root of our Y, right? Exactly the answer that we were looking for. So let's go through it one more time. This is very important. Please pay attention. So we create this A algorithm that A would play with F, but A has to, provide, instantiate this oracles that we are using. So in the beginning of the algorithm, A would choose some index T, and then just keep it as the special index. And then for every other indexes that, the forger asks for, the hash function or a signature oracle, we are able to answer those queries. And this is how we answer those queries, and we discussed that this is a valid one. But on the teeth location, we allow the attacker or forger to ask for the hash of this message, okay? And then if he ever asks, instead of following this notation to give a random value for a hash function, we put Y as the output of the hash function. We embed our hard problem over here. That's what we call it. And then, of course, the signature we don't know, because that should be the eth root of Y, and we don't know how to find it. And we hope that the forger would help us for this. So at the end, the forger would return a forgery message, some message M, and then the corresponding signature S. So with some non-negligible probability, we are saying that the only one, there is a possibility that he also provide this forgery for some other messages, so we can abort, and actually those probabilities are very low. But with very good probability. I would say the forger would provide a forgery for this index over here. And we can check that if that MT is equal to this M, right? So that is the case, then we are for sure that, okay, he provided forgery for this row. And if he ever do that, then with the relationship that we have over here, we know that S has to be the ETH root of Y, right? And if he ever provide that signature, then the signature S is going to be the X that we were looking for, right? So the ETH root of Y is actually S over here. So this is for short how or forgery, the forgery that we receive from the forger F, we would be able to use it to sign these messages. So let me go up and go through the text for you so that later there would be a better reference for you. So we start this algorithm A, and we said that he's trying to compute the ETH root. So we said that in the beginning he choose this index T from this table. So he instantiate this table and just randomly choose this T. For every other indexes other than T, then every time that the forger asks for hash function, so we choose a random value as I from Zn. We set that hash function, the output of the hash function to be S to the E mod N. And then we add this entry to the table, M, H, and then S, which is the signature. And you see that this one is the relationship, the verification message, verifying the signature function would verify this one because of the relationship we built there. And when adversary, the forger asked for the teeth query, so we are embedding our hard problem over there, and we set the hash of that T message to be Y, and add this thing to the table. And then here is the dot because we just don't know the answer. So every time now that the forger goes and asks for the signature of message M, so we just go back to the table. If that M is not M, is T, so we just return that SI, right? Over here, so that after we create this table, every time that the attacker asks for what is the signature of MR-1, we just return SR-1. We can do it for everyone, but except for this T location. So if he ever asks what is the signature for this guy, we don't know. So this is what we hope he could tell us. So in this situation, we will terminate and we say that we failed. So we probably need to run the algorithm again. And then once we find this this signature, when he returned this signature, and the signature, the M is actually exactly the MT that he queried before, then we are able to actually just compute the ETH root, and then the ETH root is just like the S that we know about, right? So so this is how we are able to do this computation. And then there are some probabilities over here that we need to take care of. We need to do the computation and make sure that what we are doing is correct. But here what we have done is for D is basically we simulated Oracle H and signature Oracle, right? Without knowing the secret, the exponent D, right? The private key T. So, and you see that we are able to do this simulation, and with that, we have answer to the questions that we receive from our attacker, from our forger, which is the attacker here. Any questions so far? Is this clear? Any place is vague? You
yes.
think? Mm-hmm.
Questions. So, I don't understand. So what we're trying, I thought we were trying to create the algorithm A, but this algorithm just kind of outsources the whole finding the answer to these imaginary forger.
Correct.
Right?
Yes.
But then we're not, like, our algorithm is not doing anything. Like, it's just asking, it's just waiting for a forger to fix it for us.
Yes, that's correct. So you're getting to the point. So, well, the point is, the forger is, we designed this RSA, full domain hash function signature scheme, right? And then we know that by the construction we are secure. But somebody says that I am able to break this crypto system. Okay. In science, you can't just have somebody to claim. It's not politic that somebody claims that, oh, I think I can break it. But right now, we already design an algorithm, and if somebody is claiming that I can break the system, you say that, okay, if you can do that, everything is ready. You see, you can just step in and you can just be this forger for us, right? And if you play your role and if you're correct that you can break the system, then with this algorithm A that I take care of all other oracles and every other computation, I can show that I am so ready for you to break anything. And then once you break, algorithm A can solve the ETH root problem, right? So we clear out every assumption and we are just waiting for this forger to show up. And if this forger says that I can forge this one, then we can use this algorithm A to solve hard assumption, RSA hard problem, right? So all we are going to conclude here is that this forger cannot exist as long as RSA is a hard problem. And if any moment anyone claims that I can break this system, well, you're more than welcome. Come over here, we run our algorithm A, you break the system. We use you to solve other problem that we couldn't solve, right? So this is like a chicken egg problem, right? Who comes first? So at least we have made this framework, we made this platform with algorithm A for whoever claims that can break this system. We don't care, you see over here, we don't care how does forger break the system, right? We know that we are responsible because we are provide him chosen signature, chosen message attack. So we are answering to the hash function, hash queries, and the signature queries of any message that the forger asks, right? We answer anything except this one place that we embed our hard problem. So how this forger algorithm works, we didn't put any restriction on that, right? We just said that, well, you do your work. As long as you can provide us the forgery, we are fine. We don't care how you work. But now we have this solid algorithm that if at any moment somebody claimed that they can forge, then we can just, plug in this person and said, okay, let's play with this algorithm A. If you break it, then I can break the RSA hard problem, right? I break the RSA hard problem, I can go ahead and do other things with it, right? So it is like a chain of these things that we are connecting to each other. If one get broken, yes, we can show that the hard assumption about RSA or the hard assumption that factoring big number is difficult is no longer difficult.
And how would we know that they're not guessing?
Oh, so we can, the point is, we don't run this game for just one input, right? If somebody say that I can forge this algorithm, they should be able to forge it for, I won't say all the time, but majority of the time, right? Otherwise, if you just guess and you win 1 out of million times, I mean, this person is not forging, he's just guessing. So you can solve one RSA problem out of, I don't know, million RSA problems that you can, if this is the RSA problem, you can solve 1 out of 1 million, right? That doesn't really make sense. It makes sense if somebody can forge and can forge most of the time, okay? Then that means that this person is really having some algorithm, knows some way to break it, really, and it's not random.
And if I don't know how they're breaking it, how am I gonna break the, well, like technically I could, like I know the forger could break the RSA, but I can't because I don't know how he did it, right?
No, that doesn't matter because as the answer that he provides for us, the S is the answer to break or RSA hard problem. This is a signature RSA problem, right? So if you break the signature, you see we have two problems. We connect them together. Where did they go? So here, the RSA hard problem is that given this E, N, and Y, compute the ETH root, right? For signature hard problem is that given E, N, and E, you only need to return a valid signature, right? A forged valid signature. And then the point is, with A, we have reduced this, connect these two problems with each other. If we connected the ETH, computing the ETH root to breaking or the RSA signature or providing a signature, a forgery. As soon as this person, how does that work? Here, as soon as this is the A and this is the forger, we don't care how forger would work. As soon as the forger provide a valid forged signature, then we can use this answer to solve or RSA problem that we care about, right? So that doesn't really matter how F is basically breaking the system. This is not our business with the algorithm that we design. And actually, it's very good that it's not our business because all we need is this forged signature, right? It makes this algorithm even a bit more solid that, no matter what technique that they use, it's okay as long as they just provide us the forgery of the message that we are looking for. And then once they do so, then actually the way that we design it, the signature is going to be the ETH root of Y that we were looking for. Okay, so in a lot of security proof, especially the signature, this embedding is a very interesting technique. Some techniques are that we have some cleverness to somehow correlate these numbers that the signatures over here look valid. We are able to do that because we are the one who can control the behavior of the hash function. We are the one because we can control the behavior of the signature oracle, right? Because we are under Oracle model, we are instantiating those two objects. So because of that, you see that we are having a lot of control on their output. So we can set their output in such a way that the signature looks valid to the eye of the forger, and that helped us to fill out this answer and answer these queries. The only thing that the second technique that we use over here is that we choose a location to embed something that we couldn't solve and hoping that the forger would solve this one for us, right? And once the forger solve this, you see that we don't even have to do other computation to compute the ETH root of Y. We just get the signature and that is already the ETH root of Y. Sometimes in some other signature schemes, you will see that after the forger returns an answer, then you need to do some other computation to answer the actual answer, the problem. And that is also has to be polynomial. But over here, you see that all we were looking for was the signature. So you may wonder, why is it so? So if you look into this correctly, the verify function over here, if I want to write it down with Y, or I'm sorry, M and S, right? So M here, you have to compute the first thing first that we should do. Okay, let me continue with the correct numbers. Number one, we have to get S to the power E mod N. And this should become the output of hash function, right? Which is going to be Y. And then we take M, we also compute the hash of M, right? Where did it go? The hash of M, which is going to be Y, right? So if we compute S correctly and we raise S to the power E, it should become the output should become hash of Y. Hash of M is basically Y. And remember, we wanted to compute the ETH root of Y. Some number like S that you raise it to the power E, mod N becomes Y. And the attacker just provided us that S that we were looking for, right? The number. And this basically concludes our proof. And so at any moment, that somebody now claims that I can break RSA signature, it is not politics. You say, okay, there we go. The platform is ready. We have the algorithm. Just do your magic. No matter what technique you use to break the system, just break it. We would just utilize your output to answer the RSA hard problem that we couldn't solve before. Right. So I think let me stop here. We have already passed your break time. So any other questions? All right. It looks like we don't have questions. So after the break time, we will come back to continue and compute the last thing, which is what is the probability that A can get these answers. Supposing that forger would not be able to forge all the time. So if we give him some probability, then we will see that what would be the effect of that on A to finish the proof. All right. So it's already almost 10. So let's come back at 10:10, let's say, and then you guys also get some break. I know this was a little bit out of word example. It was the first time you see how we cheat in the proof. And I'm saying we cheat, but technically we cheat over here, but mathematically everything sounds correct. So we kind of digest the idea and come back fresh at 10:10 to continue.